about Dyson Spheres. Now, some of you may know what these are and others not, but the basic idea is that an advanced civilization might build a great big spherical structure around and completely swallow their own star in order to capture all of the heat and light energy coming from the star to use it for their own purposes. And this we'll look at how much energy you would get by doing that and the feasibility of it and whether or not we might detect such things as a way of locating advanced alien civilizations. So let's just start by looking at the energy demands that we have here on Earth. And I thought we'd look at it just from the point of view of the graph. I'm not making any political points here or talking about global warming or any of that. I'm just saying, look what's happened since our invention of technology to our demand for a total energy budget for the world to drive that technology. It's gone in a very much an exponential rise. We're familiar with those at the moment, aren't we? We start with a small rise, but each small improvement leads to a further acceleration. And so the amount of energy that is now being consumed by the world is out of all proportion to where it was just a couple of 100 years ago. It really makes no comparison at all. And of course, one really important aspect of all of this, which is beginning to take hold at the moment, is that we're getting an ever increasing amount of energy by capturing the power of the sun using solar panels. You're seeing them more and more on the roofs of houses and great fields full of them. So I thought I'd just have a look at exactly sort of some of the numbers that go along with solar power, as it's key to our understanding of the topic for today. I thought I'd ask myself the question, and I'm sorry there's a little bit of maths here. What area of solar panels would you need to power the whole of the UK? It's a very good question. It was posed in a book that I read a few years ago when I was working on this sort of subject. And it turns out that the UK in 2019 used just over 1,600 terawatt hours of electricity. There's some very big numbers involved here. And so if we convert that from terawatt hours into joules, we get the number there, 5.9, so we can call it 6 times 10 to the power 18 joules of energy in 1 year. And if we divide it out from energy to power by dividing by the number of seconds in a year, which is 31.5 million, we get 188.5 gigawatts of power that we need to provide in order to run the UK. That's a lot of electricity. But how do we relate that to the solar panels? Well, I've got some solar panels here, and in very rough figures, each of my panels produces about 200 watts for each square meter of panel on a very sunny day. Now I'm going to round that down for convenience and call it 188.5 for reasons that will become obvious, because I'm just about to divide 188.5 times 10 to the 9 by it. So if I use 188.5, it all cancels out and I get 1 billion square meters of solar panels. That's 1,000 square kilometers, or roughly 260 square miles of land area or roof area that would need to be covered in solar panels, which is quite a lot, but it's not so much that you couldn't conceive of building it. Except, of course, we live in Britain. As astronomers, we know we don't have clear skies all the time. It's dark half the time. It's only really sunny for about a quarter of any given day, and if the clouds roll in, that rules out another great chunk of the total energy budget. So you need to probably multiply the number I had there previously by 10 in terms of overall capacity, just to deal with the fact that we don't have the right conditions all the time. And of course, you have to find some way of storing the power overnight and releasing it during the daytime, and all sorts of problems. So, of course, being good space scientists and astronomers, what we do is we say, right, let's put the solar panels in space. We'll get them above the clouds, and we'll get them, in fact, sufficiently far away from the Earth that they can orbit around it and not end up in the Earth's shadow. If we put them in a suitably inclined orbit, then they will happily orbit around the Earth and collect their power unimpeded 100% of the time. So that's a major improvement. You need roughly 10 times fewer panels to do this than if you put them on the ground, for the reasons discussed of bad weather and night mostly. But it still means you need that billion square meter array of solar panels to power the UK, and that's a lot of solar panels to lift into orbit. Secondly, you need to get the power back from your orbiting spacecraft. Now, there's some sort of magic light beam going on here in this artist's illustration. This is perhaps more like it. You would collect it, concentrate it into some ferocious laser beam, and send it back to a much more modest, smaller collecting area. And the only problem with this, of course, is that it's the plot of Diamonds Are Forever and GoldenEye and other James Bond things to put a satellite with an enormous laser up into space and point it down at the ground for nefarious purposes. And so people are somewhat concerned that such a thing would make a much better weapon than it would a power source. And what if you built such things and then they got taken over by unscrupulous hackers or something that hack into the control system? This would be very bad indeed. So it's possible, but there are downsides to it. Okay, well, we talked about what we needed to power the UK. It turns out that to do the whole of the world, well, the UK uses about 1% of the electricity budget of the whole world, and we're talking very rough numbers here. So we would need 100 times that area, so 100 billion solar panels of a meter square would do it. And 100 billion, that's well, that's 1 for every star in the galaxy, or 10 for every person on Earth in very round numbers. And you could see that if you had 10 solar panels on everybody's roof, then that maybe that would work out. Of course, I've completely ignored the fact that we don't get all of our energy from just electricity. A lot of it's coming from petrol, gas, coal and other things that directly power transport and heat and so forth. So, you know, the total energy budget for the entire civilization is a bit more than I've estimated, but only within the same factor of 10. And we're all friends here, so the factor of 10 is good enough. But the sun puts out a vast amount of energy. Only a tiny fraction of it comes our way and is available for us to capture here on Earth. And it goes back to about 1937, and this guy, Olaf Stapledon, who wrote in a novel about the idea of an advanced civilization capturing their star and building a complete shell of solar panels around it to capture the entire energy budget coming from the star and turn it into usable power for that civilization who could then do all sorts of amazing things with this nearly unlimited source of power. Now, that very much got ignored for a few years until it was picked up by someone who is much more famous in science circles, and that's Freeman Dyson, who sadly passed away in February last year. And he wrote a paper which was peer-reviewed and published in the Science Journal in 1960, called The Search for Artificial Stellar Sources of Infrared Radiation. And what he really meant was the search for these sorts of spheres. He realized that a civilization that was capturing vast amounts of energy from some source, like a star, would end up converting that energy from effectively the high temperature that it comes to them as, and leaking it away as low grade heat. And so they would have quite a strong waste heat signature in the infrared part of the spectrum, and therefore we might go and search for these the waste heat of advanced civilizations. And he referred to the waste heat from their biosphere, which people then rather misinterpreted in the light of the ideas of Stapledon, that Dyson was talking about building a proper sphere around the whole of a star. He was actually really talking about biosphere in the terms of ecosystem, as we might say today. But nevertheless, much to his chagrin, these things have become known as Dyson Spheres as a result of this. And the idea and the name really took off. Basically, the question we therefore want to answer is, what if we built a full sphere to capture all of the light output from our sun with solar panels, and tried to make use of that? And I'm just going to sort of take you through a couple of numbers on this, because we can do some maths. We've got the sun in the middle, giving out a total power output, which I'll tell you is this number here in watts, 3.8 times 10 to the 26. So that's a very big number indeed. And we can work out, given that the Earth is 150 million kilometers away from the sun, that's 1.5 times 10 to the 11 meters. And the formula for the area of a sphere is 4 pi r squared. So I've plugged that number in as r here, and I get 2.8 times 10 to the 23 square meters as the area of this this sphere. Those are big numbers, but we shouldn't be frightened of them. We can just divide out 3.8 over 2.8 and take the difference in the powers, which is just 3. 3.8 over 2.8 times 1,000 is 1,350 watts for every square meter. So for every square meter of this Dyson sphere, there's 1,300 watts available. Now, we talked about our existing solar panels giving out around about 200 watts for each square meter. And that's about right, because our solar panels are only about 20% efficient. And of course, the atmosphere blocks some of the energy coming down to the ground. So only about 1,000 watts makes it to the surface of the Earth. And our panels capture about 20% of it. So those numbers do all stack up. But now you can work out something rather interesting about this Dyson sphere. It's got this source of energy in the center, the sun, which is radiating away. Its surface is at just under 6,000 degrees Kelvin. And the Dyson sphere is catching all of that energy. And we can ask ourselves, how hot would it get? And there's a very handy formula called the Stefan-Boltzmann law, which is that the power is a constant called the Stefan-Boltzmann constant, which I've given the letter O to, times the 4th power of the temperature. So it's a simple calculation. We can plug in the value of the constant, and we can plug in 1350 for the power per square meter and work out the temperature that we would get for the radiation coming out as infrared radiation after it had penetrated the sphere. Turning the high energy radiation from the sun into low grade energy coming from a much larger sphere is really all that we're doing here. And if I plumb all those numbers in, da-di-da-di-da down here, we get a temperature of 392 Kelvin, which is 119 degrees C and is a bit toasty. You wouldn't want to try and live on a Dyson sphere built at the radius of the Earth's orbit. And that's probably a bit of a surprise, because people actually often assume that because the Dyson sphere is at the same distance as the Earth is from the sun, it would be at the same temperature. But that's not right. And I'll show you why it's not right. In fact, you'd be boiling a cup of tea on the outside of here quite comfortably, and you'd have to live further away from it in order to be at a more reasonable temperature. So why is this not giving us sort of a more earthly ambient temperature? Well, it's not because it's wrong, it's because actually when the radiation comes from the sun and strikes the Earth, it strikes one side of the Earth. In fact, the Earth is blocking a circle of radius r, which is 6,371 kilometers, the radius of the Earth. And so pi r squared again, we can work out the area of the disk of the Earth as seen from the sun, and multiply by that number of 1350 watts per square meter. And we do that here, blah, blah, and we get this big number of total watts. And if I plug that into the Stefan Boltzmann formula, I could work it all out. But a simpler way of looking at it is that actually what then happens is that the Earth then radiates the energy out from the whole surface area of the sphere. So particularly the hot spot directly under the sun, right in the middle here, picks up lots of heat, and then the Earth turns round and it's going to radiate it from the far side. So although we're catching an area of pi r squared, the whole surface of the sphere is radiating it away equally after the atmosphere and the oceans have spread it around. And that corresponds to 4 pi r squared for the formula for the area of a surface area of a sphere. So the surface area of the sphere is exactly 4 times the surface area of the disk that the sun sees. And so in fact, the area that's doing the radiating is 4 times as much as the area that's doing the catching. That's a very simple way of doing it. So we can plug in a factor of 1/4 into our calculations, and the quarter goes in there into the same numbers, and we get 277.7 degrees Kelvin, which is just 4.7 degrees C. And that's a much closer match actually to the average temperature across the whole of the Earth, showing that this really does work as a way of working out what your temperature is. In fact, of course, things get more complicated because we're not catering for all of the different factors, the reflectivity of the clouds versus the oceans versus ice. All of these things play a small part, and of course the greenhouse effect of the carbon dioxide of the water in our atmosphere not letting the infrared radiate to space freely has an effect as well, and changes the balance of things. But one important thing that I thought I would just mention at this point is, if an alien civilization was looking for Earth and looking to see whether or not there was anything interesting about it, it could look at its spectrum and see the light coming from the Earth, and it would see some rather curious things. Rather than a uniform temperature of around 300 degrees Kelvin, 277, whatever number you choose to come up with, it would have some rather strange features because a lot of the vegetation on the Earth absorbs the red and the blue light and reflects only the green and the infrared. And so the forests of the Earth give the spectrum of the Earth quite an interesting feature. You can see it here. This is all part of the infrared spectrum from about 0.8 down, and the visible spectrum is this little bit here. And you can see this is the blue being absorbed by plants, the green is rejected, and then the red is absorbed. And then further on down here, we get different absorptions by water. And in fact, we use this when studying the Earth with Earth orbiting satellites to work out where crops are growing. And you can even tell the difference between the crops because different ones have different shapes and ratios for their absorption spectrum. So if we can study it, so could an alien. Anyway, so we've worked out that that's why the Earth isn't at 119 degrees centigrade, is because it's playing the trick of catching the light and radiating it over 4 times the area. But the Dyson sphere can't do that. The surface area of the sphere is the catcher and the radiator. And I just wanted to point out the ratio of the surface area of the Earth to that of the Dyson sphere. And it's tiny, of course. The Earth, you'd need 2 billion Earths to have the same area that we would be dealing with. So the Dyson sphere is going to catch 2 billion times the amount of energy. And so that would certainly solve your civilization's energy budget for quite some time to come. A factor of 2 billion times the total available solar energy of the Earth. But is this whole thing completely mad? Is it actually feasible? And to answer that, you need to look at a few sort of engineering type questions. Just how much material would you need to build a sphere that big? What would you build it out of? Would it be strong enough to hold itself together? And what would it do to gravity to have that much material in a giant sphere like that? And some of these are quite easy questions to tackle. The first one, how much mass, is good because we already worked out the surface area, and we could just say, well, let's make it 1 meter thick. And so we can actually just multiply by 1 and get the volume. That's a very straightforward approximation. And if we assumed that it was made of material with the same average density of the Earth, we can multiply that out and get a mass, which works out to 1,500 times 10 to the 24 kilograms. Absolutely enormous. How much is that? Well, the total mass of the Earth is 6 times 10 to the 24 kilograms. So you'd have to completely destroy the Earth. In fact, you'd have to take 250 planet Earths and completely use up all of their mass in order to build one of these things. I suggest that's probably making the point that this is completely ridiculous idea, actually. You might argue you could make it thinner than a meter, in which case, you know, it wouldn't be very strong, I don't suppose. Even a meter is pushing your luck, I think. But even if you decided to make it only 1 millimeter thick, you'd need something the mass of a quarter of the mass of the Earth. So you'd have to destroy Mars or something like that to build it. And if it was going to be even thinner than that, well, then maybe a large asteroid would do the job. But I can't see us making anything thinner than really a meter or so, and having it have any strength at all. I mean, it's got to put up with being hit by the occasional asteroid. It's got all sorts of interesting problems to do with the gravity of Jupiter pulling on it and trying to warp it and distort it. Maybe we should take Jupiter apart and use that, you know. Still not enough, really. The other problem is, will it hold together? And the answer to that is no. No known material would have enough strength to resist the crushing stress that such a sphere would be under due to the gravity of the sun pulling inwards on it. And the slightest inward deformation would suddenly tear the whole thing apart. And so, yes, that gravity of Jupiter warping it would be a real disaster. I think it's just orders of thousands of times stronger that we would need to make it if we pursued the mathematics on that. What about the effect on gravity? Well, Newton showed something rather interesting, which is that inside a hollow shell of material, the gravity of the material that makes up the shell all cancels out. If you think about it, you're right at the center where one of those red dots is. You're equidistant from all of the material in the shell, and so the gravity of each atom of the shell is pulling towards it on you, and they're equal in every possible direction, and so there is no net force. Now, you might think that at the other positions marked that would be out of balance, but Newton showed, and we could look at the maths, but I'm not going to, that at every possible position inside the shell, it still cancels out, because you might be near to some of this mass, but you're now much further away from a larger amount of the mass, and it exactly cancels out. There's a tour de force by Newton in using his maths to show that. And so there's no net gravity at all inside the sphere. And this is a problem because it would lead to the sun being free to wander around. There would be nothing keeping the sun stable in the center. And so if there were any sort of gravitational nudges going on from Jupiter or whatever that would nudge the sphere, they wouldn't be transmitted through to nudging the sun, and it would wander off and eventually collide with the outside of the sphere, and that would make a terrible mess. And if your solution to this is to put some sort of magic thrusters on the sphere to keep it centered with the sun in the middle, bear in mind you're trying to shift something that has 250 times the mass of the Earth. So trying to move it around needs an enormous amount of power. You often also see diagrams like this in connection with Dyson spheres, where people have migrated from the Earth and are now living on a city on the outside of the sphere. Well, I think I've already shown that you'd have to build the sphere a bit bigger. You'd have to build it with a greater diameter in order that the surface temperature wasn't above boiling point, and move it out a bit, and we could work out just how much further out from the sun you'd have to go for that to happen. Wouldn't be that far, actually. It's a small adjustment. It's also interesting, though, that the surface gravity of such a city built on the outside of a Dyson sphere would be a bit of a problem, because the gravity of the sphere itself, if you work that out, ignoring the sun in the center, you can work out the mass to be 250 times the mass of the Earth, and it would act downwards on you. And again, Newton showed that if you're outside the sphere, you can model it perfectly as if all that mass is concentrated at the center. And so the force pulling you down would be as if someone had put 250 Earth masses 150 million kilometers away from you. And any of our young astronomers can soon do the calculation with Newton's formula for gravity and show that you'd actually have a very tiny amount of gravity pulling you down onto the Earth. In fact, with the sun in the center, the sun would be the dominant feature there, because it would dwarf the 250 Earth masses. It's about 300,000 Earth masses. So you would be solely really subject to the solar gravity pulling inwards. And that would be about 1/20th of the gravity that we feel whilst wandering around on the surface of the Earth. So these sorts of cities would certainly not be somewhere where you would be growing trees like this. You'd have a real problem holding on to an atmosphere for a start. So what is the solution? Perhaps rather than a full sphere, which would catch 2 billion times the energy budget of the whole of the Earth, or 1 trillion times the current Earth requirement for energy, perhaps that's overkill. Perhaps we should aim for something a bit more modest. What about a ring around the sun, perhaps slightly further out than the Earth's orbit? That would be a much more practical proposition, or some sort of polyhedral arrangement to try and get some rigidity into the system. Maybe that would be more plausible, as shown in the artist's impression here, where they've gone for a sort of triangular grid, making up an approximate sphere. And some of those solutions are a lot more plausible than capturing the whole of the energy of the star. You would only catch a fraction of it, but it'd still be a very, very useful amount to any sort of advanced civilization. So these sorts of things are a bit more plausible. Even more plausible, though, is just not to bother making it a rigid structure, and to put lots and lots of solar panel satellites in orbit. And the reason for this is you can start with one and you can just keep adding them and building up. You don't have to build the whole ring or the whole structure to make it stable. So you could surround your star in enormous numbers of solar panels, provided you could beam the energy back somehow. But actually, NASA have already done an experiment like this of putting a giant solar panel in space and beaming the energy back to the Earth. And that does work. It has the James Bond death ray problem that I mentioned earlier, but and of course it might go wrong even if it wasn't deliberately misaimed. It might wander off track and fry some part of the Earth that you cared about. But and with tens of millions of these up there, probability of one of them running amok like that starts to get quite high. So you'd have to have a lot of safeguards built in. So given that these sorts of partial structures, either orbiting or rigid, are a bit more plausible, could we find anything like this? What would it look like from our point of view? And this all came to the fore in about 5 years ago, in 2016, with the discovery of Tabbys Star. As part of the Kepler Space Telescope's Planet Hunters mission, the Citizen Science Project, a number of amateur astronomers spotted a star in the Kepler data that showed a very strange curve in its brightness. It was suddenly dimming and then coming back to full brightness in a very, very erratic way. What, of course, the program was really looking for was the regular dips caused by a planet crossing the line of sight and blocking a fixed proportion of the starlight while it did it on a regular basis. And I used some of the data, and I found a planet back in 2012, I think it was, that did precisely that every 397 days. And you got a very regular dip in the light curve. But this particular star has an absolutely wild light curve, with the dimming going down, taking it down to 20% or more of the light of the star being blocked. Now, the planet that I found was a Neptune-sized planet, and it blocked 0.3% of the starlight, because stars are really rather large compared to planets. So something blocking 20 or more % of the light has to be very big indeed. Now, this star was then studied by an astronomer out in the US called Tabithas Star, and we now call it Tabbys Star because her surname's so hard to pronounce. There's the light curve for it, which looks like nothing we'd ever seen before, with these enormous dips going down. As I said, an individual dip like this one here might correspond to a planet, but it's got these weird side dips, and it doesn't look like anything at all. And some very broad dips, and some that go very deep indeed. And it keeps on doing this. It keeps on producing these erratic patterns that no one's able to see any sort of repeating structure to. And so the idea was suggested that maybe this was a partial Dyson sphere, perhaps under construction. The star is an F-type star, a little bit hotter than our sun, burning a little bit more brightly. And perhaps there's, an alien race there deciding to take the next step and start to build a megastructure to capture a lot of that starlight and use it for their own purposes. And perhaps what we're seeing is partially constructed arrays of solar panels passing in front of the star and blocking really rather large proportions of the light as they sweep past. Well, maybe that's the case. In fact, we've been searching since Dyson's paper in the 1960s for Dyson spheres, looking to see if we could detect full ones, even though we thought that they were probably impossible to build, because who knows, ancient people built the pyramids and we still haven't quite explained that. And so the question really is, what would these things look like? And is Tabbys Star a representative case of what we would expect to see? Well, a full Dyson sphere, you wouldn't see the star at all, and all of the star's high energy light would have been converted into heat radiation. And to understand that, we have to look at what heat radiation looks like. Very much you get a curve, a slightly skewed distribution curve like this, a long tail into the infrared and a peak, and then a maximum cutoff point. And these curves are characteristic of an object at a given temperature. So if you find the peak of, like this tallest graph has a peak at 7,000 Kelvin, that will be in the visible part of the spectrum and will be a blue-white coloured star with the light coming out here. The sun is down here, where it's giving out middle range wavelengths in the sort of green and early blue, and red dwarf stars, they're red because the only visible light that you get is really this last little bit here, because they're at about 3,000 degrees. But you always get this same shape curve. It's just that the height of the peak declines with temperature, and the position of the peak moves to the right on the graph as you cool the object down. So if you see a curve like this, you can easily work out the temperature. So there it is again for the sun with its light curve. And here's the one for the Earth. That's obviously much lower amount of heat that you get coming off the Earth, but the maximum is at 288 degrees Kelvin, which is actually the average temperature of the Earth, and that's where this peak is here. I discussed earlier that if you looked at that in great detail, you would see differences caused by things like the forests, with them absorbing some of the light in the green and some of the infrared light as well. So if you looked at a partial or a full Dyson sphere, you would simply see all of the energy of its star coming out as infrared energy at around 300 degrees Kelvin. So you'd get an infrared light curve, which would have a peak corresponding to the wavelength for 300 degrees Kelvin. And the odd thing about it would be very, very bright. It would be 1 billion times brighter than the heat output from the Earth, because the total star energy is trying to come out from this object. So it would be a very, very bright infrared source. And of course, back in the 60s, when Freeman Dyson suggested these things be searched for, we didn't have infrared telescopes above the atmosphere able to look for these sorts of things. We do now have some very good ones, and indeed the James Webb Space Telescope that is in the process of deployment, and so far so good. It's seemingly all going well last time I looked. It's going to have great capability at looking at infrared objects, and so this is a candidate for things we might go and look for. It wouldn't look really like anything much else. James Webb would be able to tell the difference between, for example, a dust ring around a star and a Dyson sphere. And the reason is because the dust ring is going to block some wavelengths of light completely and not others. The longer wavelength light will just go straight through the dust and not be absorbed by it. But a solid Dyson sphere is going to block all of that. And so you get a perfect black body curve in the spectrum. But partial swarms, much more complicated, because the starlight's still going to get through, and you would see that. You would also see the heat signature coming from the warmed up bits of the orbiting satellites, or the fragments of the partial sphere. And so you would see two peaks, one from the star and one from the material of the Dyson sphere itself down in the infrared. And that's actually what we could go and look for with the James Webb telescope, looking at these light curves to see if we can see that excess infrared hump in the spectrum that is indicative of something capturing energy from the star and dumping it as waste heat. So that's really what we would like to go and look for with it. Now, the Gaia Space Telescope's been up there for a few years now and has been measuring 1 billion stars, looking at their brightness, their distance, and their color. And their color, of course, tells us their temperature by that black body relationship. And this is just also just the right data to go and study what's going on out there and see if we can spot any partial Dyson spheres. And the way you would do it is to plot out the Hertzsprung-Russell diagram, so brightness going up here and temperature or color going across the bottom here. So these down here would be the cool red dwarf stars, the sun-like stars in the middle, and the hot blue stars in the top left. And this is the data for Gaia from that, all plotted on one chart. And what we would see for a partial Dyson sphere is a star that was not on that diagonal line, the main sequence, because the stars, some of the stars' light energy would be being trapped and re-radiated off the chart as infrared. And so we would see stars that were somewhat below the diagonal line of the main sequence of ordinary stars that were just sitting there below that line and having a temperature that doesn't properly correspond to their brightness. And look, here they are: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 candidates down here that are off the beaten track. All of these are proper ordinary stars. They vary slightly because of things like how what proportion of the heavier elements they have in them, which is what is making that line broader than just a single line, plus the fact that it's the combined traces from not only the Milky Way, but some of the dwarf galaxies that the Milky Way has eaten. But there are certainly a few candidate stars down here that are below the line. They're not giving out as much light as their temperature would suggest. So these are candidates for alien megastructure interference, or partial Dyson spheres, as we would call it. These ones over here, these are white dwarfs. We understand them. We don't need to worry about them. They're the remains of dead stars. And what's going on here is these are all the red giants being formed as stars run out of their ordinary ability to make hydrogen into helium by nuclear fusion. And the reason there's several thin traces in there, again, is because the Milky Way has eaten smaller galaxies in the past. And so we've got a number of different populations and different ages of stars all overlaid there. So what we could do is look at these stars, these 10 here, that have fallen below the main sequence with an infrared telescope and see if they are producing an excess in the infrared that matches the amount of missing energy that would have put them back onto the main sequence. We haven't found that that is the case yet, but it's actually a very difficult measurement to do in the infrared. And again, the James Webb Space Telescope is going to target some of these. And that's one of the things that we might learn about as we get the thing working. Of course, if they're not Dyson spheres, then it begs the other interesting question: what are they? What are these weird stars that are misbehaving, not sitting on the main sequence and being either too hot for their brightness or too bright for their temperature, depending on your point of view, or not bright enough for their temperature, depending on your point of view? You know, why are they dimmer than their temperature suggests, and what's going on with them? So they're very interesting to try and understand in any event, even if it's not aliens. So as I said, James Webb will go and look at these and we'll get turned to them at some point, and hopefully that won't be too far away. Now, again, I think James Webb's also going to have another look at Tabbys Star, but the latest results on this are that I'm afraid we're not in the top picture situation, but it's more likely that we're in the bottom situation with a whole host of a swarm of comets that are orbiting around the main star with very long, thick tails that are blocking the starlight. And it's those cometary tails that are responsible for the dimming of the starlight in the very erratic manner. The reason we believe this is that we've looked at the dimming in different wavelengths now, and the dimming in the visible part of the spectrum is different to that in the ultraviolet and in the infrared. and in particular, it's much less apparent in the infrared, and the infrared tends to go straight through dust clouds. So it's likely that these are the effects of dust that are blocking the starlight, but they're not blocking the heat radiation, the infrared. And so I'm afraid Tabbys Star looks less likely to be a Dyson Sphere. And another factor about it that's recently been discovered is it has a binary companion in the form of a red dwarf star orbiting around quite a long way away, 880 AU. That's a lot further out than Neptune, which is 30 AU from our star. So it's really quite a big orbit. But it could be that this little red dwarf companion is disrupting the star's Oort cloud, the cloud of leftover icy material that is turning in these items of the Oort cloud into comets plummeting into the inner solar system, perhaps in a situation similar to happened in our solar system with the late heavy bombardment that might have been responsible for delivering a lot of the water to the Earth, with all these dirty snowballs coming into the inner part of the solar system. In our case, it was an interaction between Jupiter and Saturn that caused that, but here it might be this binary star that is perhaps hurling comets into the inner reaches of the solar system of Tabbys Star and causing all this excitement here on Earth when we thought we might have discovered evidence of aliens. So I'm afraid I'm going to bring the talk to an end there and just say it's never aliens until it's proved to be aliens. And in this case, it wasn't. So better luck next time.